So we're going to begin a discussion about finding the area under the curve. And what we're going to learn later on is that an integral, a definite integral, will give us the calculation for the area under the curve by applying something called the fundamental theorem of calculus. But what we're going to do here is we're going to approximate the area under the curve by drawing rectangles and finding the areas of rectangles. So it's very simple. You find the area of a rectangle by multiplying length times width. And so what we're doing here is we're going to look at three types of sums in these examples here and in these diagrams. And then we're going to work out three problems, and they're very basic, very simple, but it'll give you the gist of what it is that you're doing. All right. Now, these are covered in a lot of math textbooks, but really not very popular. There's another set of sums, and that'll be for another video. But the gist here is that we're talking about something called Riemann sums. And so I'm not going to mention Riemann sums other than talk about it at that instant, but we're going to be talking here about upper sums and lower sums and what exactly that means. So what happens here is if you are asked to look at a particular function over an interval, in this case, looking at these two graphs, we've got 1 minus x squared, and let me zoom in just a little bit for you so you can just look at that one. We're looking at these two. We're looking in letter A from 0 to 1. And suppose in this example they said, well, use two rectangles to approximate the area under the curve using an upper sum. So if you're going from 0 to 1, you'd have to cut it in half to create two rectangles, first of all. So the distance here, the change in x is going to be 0.5 and 0.5. So that right there is what I call your delta x. Okay, so that being said, the upper sum takes a look at that rectangle and it uses the maximal height. Okay, so the greatest location on this graph here happens to be at 1. Okay, for that rectangle. So the height of this rectangle is 1 unit. And then we look at the next one. All right, we are again looking at the second rectangle from 0.5 to 1 on x, but the y value is going to be the maximal height there. So the maximal height there is found at 3/4, so that's 0.75, and that is the height there. Again, the width is 0.5. So if you're looking at those two rectangles, that is the maximal height. If we were looking at the minimal height, well, it'd be a different case. All right, but at any rate, all right, you're looking from this spot to this spot. This is the maximal, so this is the upper. This one right here would represent the lower. So, okay, so this is the minimal value. All right, but we'll get to the lower sum in just a minute. All right, so let me erase this. What I'm going to point out is that this graph over here is exactly the same function. All right. However, this one is divided into 4 intervals, so your delta x is slightly different. All right, here your delta x represents a quarter. All right, and all of these delta x's actually represent a quarter. All right, so that's what you end up finding here when you're looking at this. And what happens is the more you can subdivide your graph, okay, the more, in other words, the more rectangles you can inscribe or overlay, the closer you will be to the more approximate area. Okay, so just keep that in mind. So now let's take a look at something called the lower sum and then the middle sum. Well, the lower sum, if you see here, this one was subdivided into 4 regions. Of course, you might only be seeing 3 rectangles, but notice here at 0 to 0.25, for example. Let me pick a different color, maybe red. So if you look along this area, this is the maximal and this is the minimal value. So in a lower sum, they want you to use the minimal value. So in this case, the height would be 15 out of 16. All right. And then notice here, as you look at the next region, and I'll color that in green, This right here is the minimal value, and so that right there is 3/4, and so forth and so on. So that's basically how you would determine the height. Your delta x is nothing different, okay? Your delta x here, and I'll write this out for you, your delta x is going to be your final spot, your final x value, minus your initial x value, divided by the number of rectangles that you need. Okay? That's how you figure out delta x. Now, if you look here, there is actually one spot right there, and I'm going to color this one in blue. All right? Now, if you notice, 7/16 is the maximal. The minimal value is 0. So that's why this one is actually flat. It has an area of 0, if you will. Okay? And then, of course, moving on over here to the middle sum, if we look at the middle sum value, if you notice here, this one is also divided into four rectangles, if you will. And you use the value that is in the middle, okay? So not the minimal value. So this one was the minimal value. This one was the maximal value. You use whatever is in the dead center. And that's why they're using the height, reaching the middle of the function value. So it is necessary in this case to find out what is in between your delta x. So here was my delta x of 1/4. And you actually have to find out what the x value is. And in this case, they found it to be 1/8. All right, and that happens to be the case for the rest of these as well. So we're going to take this knowledge and we're going to apply it to some problem solving here, to some examples, and they're actually fairly easy. So let's go ahead and take a look. So let's look at the first one. And I provided these graphics here to help with the drawing because I'm terrible at drawing. All right, you'll see when you see my rectangles. So if we're going to look at this one, it says x squared. So this is the graph of x squared between 0 and 4. So here's 0 and here's 4. All right, x squared, all right, between 0 and 4 using a lower sum with two rectangles of equal width. So what is our delta x in this case? It is 4 minus 0 divided by how many rectangles? 2. So our delta x is going to be 4/2, which is 2. So every 2 units, we're going to have a rectangle. So that's interesting. All right, now it's a lower sum. So let me highlight that here. Lower sum, that's important. Okay, because it tells me that if I am analyzing my graph right in this spot, the lower sum will be the minimal value. So I'm going to be looking here at that value at 0. So right here, I actually have a rectangle, but if you think about it, the area of that is going to be 0. So we're good there. Now we look at the next spot. Okay, so let's take a look at the next one from 2 to 4. And I'm going to kind of trace the curve here. And we're looking at, again, the minimal value from 2 to 4. And the minimal value is right here at the value 4. So what we're going to do is we're going to inscribe another rectangle right here, and what we're going to do is we're going to add these areas. So the area of the first one is 0, so that is of no consequence to me. All right, so I really don't need to include it, but what I do want to include is this area right here under the curve. All right, now let's think about this for a second. If you're doing a simple geometry problem, all right, the height here is 4 units. All right, and the width here, I know it looks a lot bigger, but the steps are different. The width here is 2 units. So if you count 4 times 2, or if you multiply rather, you get an area of 8 units. So what we would do is multiply 4 times 2. And of course, we would have added the 0 at the very beginning because the height there is 0, so that's 0. So we end up with 8 units squared. And that is the area of under the curve, or the approximation for the area under the curve, given the conditions we were initially given. All right, now let's take a look at another example. All right, really nice, clean example here. Number 2, and then we'll look at our last one, number 3. So number 2, let me highlight what we're looking for here, an upper sum. All right, so we've got an upper sum here. And what I'm going to again do is I'm going to trace the function. So what we're going to do is we're going to write out what it is that we need. We need delta x, all right, that is from 2 to 0, or 0 to 2 rather, and cut in half, 2 rectangles. So our delta x then is going to be 1. So right here is kind of our center, if you will, of the graph, 1. And we're going to draw the rectangles now. So let's trace over it from 0 to 1. If it's an upper sum, that means that this point is the point that I'm looking at. That means that my rectangle needs to be at that height. Okay. All right, there's one rectangle. And now we're going to look at the next spot, and that's this spot right here. And if you're doing the upper sum, that means you're going to be looking at this spot and not the other. All right, and so we draw another rectangle there. All right, line it up. Okay, so as you can see, this one is actually an overestimate of the area. All right, but we're going to get basically the area for all of this right here. Okay, it is an overestimate of the area. And in another video, in the next video that I'm making about Riemann sums, we'll talk about that as well. Okay, so we're looking for this area here. There we go. I'm kind of just shading it in for you so you can kind of see. And then this one right here. All right, and then we'll talk about the dimensions of this. So this one right here happens to be 1 unit high and 1 unit wide. And then the next rectangle happens to be 4 units high but 1 unit wide. So what we do is we are going to multiply, in this case, 1 times 1, and let me actually switch colors so I can stick with black here. 1 times 1 plus, okay, because we need to take the sum of all of the rectangles, the sum of the areas of the rectangles rather, and 4 times 1. All right, so what do we get? We get 1 plus 4, which is 5. So we will say here then the area is 5 square units. All right, and that's what that one looks like right there. All right, now let's take a look at the last one and see how this one is a little bit different. This one right here is asking for the midpoint rule. The midpoint rule. All right, so we're looking at f of x again equals x squared, but in this case from 0 to 3. All right, and let's go ahead and write out what our delta x is. In this case, we're going to say 3 minus 0, and then they want us to use 2 rectangles. So 2 rectangles. So 3 over 2 is 1.5. So what I'm going to do, I've got 1.5 right here marked off for you, but they want us to find the area under the curve using the midpoint rule. So I actually have to look in between 0 and 1.5 and 1.5 and 3. And that's where I get these values that I'm going to highlight for you right there. Okay, so what we do is we're going to use this value to draw our rectangle. So right here where it touches the graph, all right, let's see if I can get it. Right there, there's one rectangle. And then we're going to go up over here, center there, center there. There's another rectangle. So this right here is obviously, I mean, it could be close to, if you count for the missing area up near the top, we might account for it with the overestimate here in this second rectangle. So what we're doing here is we're calculating, or we're going to calculate anyway, the area of this rectangle and the first rectangle, which is down here at the bottom. All right. Now, how do you find the y values? Well, it's really simple. You just plug them into your calculator. You can do them by hand. It doesn't really matter. But the function is x squared, so you'd plug in 0.75 squared. And that's how you'd get this first value here. And this first value would be something like 0.5625. So let me write that out here, 0.5625. And then the second value here would give you something a little over 5. Okay, so that's 5.0625 is what you would get there. All right, so those right there provide the heights of the rectangle. Now we worry about the width of the rectangle. Well, each of the widths is actually 1.5 units. 1.5 units. So that's what we figure we need to multiply. So we're going to take 1.5 and we're going to multiply it first by the 0.5625. All right. And then we're going to add this area of the second rectangle, which is again 1.5, but in this case multiplied by 5.0625, which is what you get again when you do 2.25 squared. All right. So we've got that. You could do it all together on the calculator. I'll just write out the actual individual calculations for you, and then you'll see how I got the final result. The final result being 8.4375 units squared. Okay, so maybe this video was a little bit long-winded for you. Hopefully you were able to fast forward through to exactly what it is you needed. At any rate, I hope you got a greater understanding of the lower, upper, and mid sums, and how you can apply it to find the area under a curve. So as always, if this video was helpful, remember, like and subscribe.